Thank you very much, Gary, for a great start and a great talk. So I would like to kind of follow up on this. Gary talked a lot about very many technologies, particularly that are in applications that I would say are more digital. And I'm going to take a look at one that are more RF analog and mixed signal. Let me see, where did the remote go? Okay, so first I'm going to start out by just talking a little bit about the industry and how it's been sort of transformed by things that have been happening in the communications market. And then I'm going to talk a little bit about our fab in our 200 millimeter fab, which are larger lithographic nodes, and talk about how we have transitioned that fab to adapt to a changing marketplace. So the idea here is we're going to start out with products and marketplaces and sort of work ourselves back to technology. And then I'm going to show you a little bit about how we change some of those technologies to make them really effective in that marketplace. And then discuss a little bit about some of the products that has come as a result of that. So first let's take a look at the trends. So this is a picture that people have seen in probably a lot of conferences and publications, and it's essentially the growth of wireless devices. Now, if you this is maybe a little bit older slide. As it gets more and more updated, you find more and more tablet growth and even more kind of explosive growth in it. But essentially, you see this transition from cordless phones, 1G, 2G, moving into 3G and moving into long-term evolution and essentially seeing just the number of handsets in the world taking off. So now let's talk a little bit about what those handsets are and how they're changing in terms of the standards and data rates. So today people want to be more and more mobile. Okay, they want, it's not enough anymore to sit at a computer with an Ethernet cable plugged in. People really want to have that same capability in a more mobile format. So over time, what we've seen happening is as people have transitioned the ability to get data on their cell phones versus sitting still, sort of a personal area, they wanted these kind of high-speed data rates really on their mobile devices. So you can see here that as you go up in sort of mobility, getting even to vehicles here, that the data rates all sort of compress and get much lower. So what we see now in emerging standards, we started out with GSM, GPRS, Edge, moved to UMTS, 3G, people have 3G phones now, 4Gs are just becoming available, and now there's a lot of discussion about long-term evolution. And if you look at it, some of these, beyond here, people are even talking about higher frequency standards in the cell phones in order to really pick up the data rate. Now, that data rate has an impact, okay? And that data rate and that hunger for data really means you're driving a lot of mobile data. So similarly to the handsets, the mobile data is taking off at an even more explosive rate because every time you enable one of these standards that puts a higher data rate, and the handsets themselves are essentially exploding with tablets and other forms, these data rates just get higher and higher. So how do you actually address those data rates? Now, one of the things I want to talk about is just one specific segment, which is sort of the wireless segment. And essentially what we're going to see is not only do the devices themselves have to support this exploding data, but even just dealing with all of that traffic, period, that also has to be addressed. And what you're going to see today is a little bit about how we've taken some of those important issues and just solutioned them with really older technologies by being able to adapt them. So this is our IBM's view of our specialty foundries. So these are our 200 millimeter technologies, and that's basically 90 nanometer and larger lithographic nodes. And what you see in this is 4 segments. So again, we saw the explosive growth in the handsets, And what we're going to look at in some of these handsets is what kind of technologies are required. Well, if you take a phone apart, you'll see that a lot of these are front-end modules in there, different radio standards and transceivers. So we have we've really explored this area here with our SOI and silicon germanium. We also have the high-performance RF analog and mixed signal. So these are, you're driving your car down the road, you want radar for assistance while you're driving. So that's these kind of high-performance RF analog mixed signal. Power management. People want smarter planet sort of applications where you want to control the lights in your home wirelessly, control more things wirelessly versus wired and switches, and some specialty manufacturing. Now, so those are the sort of segments that we really wanted to change our fab. And if a fab is built, I mean, I think you want to make it very adaptable, and whatever we see today, it's going to be different tomorrow. So we have, over time, really transitioned our fab in Burlington, Vermont. When this fab was first created, it was essentially serving internal needs. It was making processor chips, and it was making memory chips. At one point in time, actually, there were probably more memory made in Burlington, Vermont than probably any other place in the world, because we really pioneered a lot of the DRAM production technology, early DRAM production technology. So what you see is the segments were consumer, and it was this whole thing of IT and our base technologies for processors. Now, over time, the processors migrated to more advanced nodes and went to 300 millimeter buildings. And this just is 2007. This has basically gone down to almost nothing. If we take a look at these memory chips and other sort of chips like that, these things have also declined. So what has really emerged is the consumer space. And today, this consumer space is basically 80 to 90% of the fab. So as this changed, we changed our fab not in the sense of the tools that were there, but in adding different aspects to it to meet the application. So it gives this theme of what's happening out there in the marketplace, change how you do things in order to meet those demands, and be always adaptive and flexible when you're doing this. So this just shows a little bit about that contrast. We started out with more of a processor technology mix. So this scaled with lithography. Gary's been talking about scaling. We CMOS device innovation for performance as scaling ran into difficulty. Lower voltage, new materials, and he went through all that. In analog and mixed signal, you have something very different. And in RF analog and mixed signal, you find it doesn't always shrink that well with lithography. So going to more advanced nodes doesn't always buy you a lot. And the reason for that is because RF analog and mixed signal chips tend to have a lot of inductors. They tend to have a lot of capacitors. These things tend to be larger elements, and they don't scale well with lithography. So they don't shrink very well. You are constantly doing new structures for power management. These don't tend to be small. Power transistors tend to be fairly large device, and you need larger drift regions in order to drop that voltage. So it doesn't scale. And the emphasis becomes client collaboration. Find out what they need and have very accurate RF analog and mixed signal. So instead of shrinking everything lithographically and emphasis on new materials and leading edge innovation, we're really trying to find out how what people are doing, what they need, and how to change what we have to mix, to meet their demand. So this is our silicon technology mix. It's in the 200 millimeter fab. And I think it's a good case for how you change things to really meet the applications out there. So here's lithographic node. You can see here's half micron, 0.35, quarter micron. This is 180, 130, and 90. Now, compared to the modern technologies that are really in the high-performance digital, these are very large lithographic nodes. I can tell you that the richest node we have today and the largest demand is at 180 and 350. So these are large nodes, and I'm going to show you some of the applications that you probably have in your pocket. You just didn't know it. So so take the base CMOS, We differentiate that CMOS by adding in RF enablement, very accurate models, so that you can make RF products with it. And then on top of that, we start adding other aspects, like a silicon germanium transistor. So you could use, well, bipolar transistors for some higher performance. So every time we have a base, we make an RF CMOS, we make a silicon germanium derivative, we can make a high voltage on that, and we did something else at 0.18, which is we combined it with SOI to make a 7RF SOI. These technologies here, basically digital logic for controllers, SOI for switches, and these 0.35 micron silicon germanium power amplifiers, these are the three sort of hottest products we're doing today. So you don't need advanced nodes to make very, very good products. This is essentially where I hail from. It's Burlington, Vermont, just shows the fab. And again, we have specialty technologies of RF CMOS, silicon germanium, high voltage, ASICs, and the emphasis is on larger lithographic node. Now here's a cell phone, a picture of a cell phone, and let's take a look at some of the different elements of the cell phone. So we can see we have a baseband processor. That's where all of the advanced digital technology is. And there's memory, flash, application processors. So this is where a lot of the leading edge is. And certainly Gary described the IBM content here. So if you take a look at the other parts of the phone, a lot of it is really these basically radios. You see transceiver, you see Wi-Fi, you see power amplifiers, TV tuners, you see all sorts of different cellular standards. Of course, there's a digital chip here with the baseband, but there's an analog baseband. So much of the phone is really radios. And if you look at this, they're implemented in RF SOI and silicon germanium, these larger lithographic nodes. So let's take an example of a cell phone. So I just picked one that was pervasive out there, which is the iPhone. And if you start taking this thing apart, you could go to many websites. I'll actually show you tear down exactly what kind of products in it. You'll see that they have radios. And if you take the radio modules apart, you'll see that these are in these things called front-end module, power amplifier modules. If you take these things apart, you basically have four kind of components. You have a power amplifier, a CMOS logic part that essentially controls the power amplifier, making it more efficient and controlling how it works, and also controlling how it works with the other parts like switches. So switches go between different bands, different protocols, etc. And then you have filters and duplexers. When we first started working in this segment, all of these parts were heterogeneous, except for the controller, which was CMOS. They were all in 3.5 technologies. So what that really meant was we were going in with silicon to something that was largely 3.5 for performance. And what we've shown is you can take silicon, a silicon fab, you can make this a pervasive technology and do almost all the applications in this cellular phone.